You know, when we think about big breakthroughs in AI, we usually imagine these massive, complex new models that take tons of power to run. But what if I told you one of the next huge leaps forward could come from changing just a single line of code? Seriously, that's the question we're digging into today. We're going to break down a paper that found a simple, almost shockingly elegant tweak to a core AI process, and the results are pretty incredible. Okay, so to get this, we first have to talk about something called the attention mechanism. This is basically the secret sauce behind huge models like GPT-4. It's how an AI decides which parts of the information it's looking at are the most important. It's literally how it focuses its attention. So, how does this AI focus actually work right now? Well, for years, pretty much every major AI model you've ever heard of has been built on the exact same foundational idea. It's called dot product attention, or just DPA for short. And this has been the gold standard for a long time. It's been wildly successful, but, and this is a big but, it has a fundamental limitation baked right into its geometry. So here's the thing about standard DPA. It's kind of black and white. Think of it like this. If two signals are pointing in the same direction, the model goes, aha, a match, and pays high attention. But if they're pointing in opposite directions, it basically treats it as a total mismatch and ignores it. It's really good at spotting agreement, but that's about it. And that simple rule, high attention for things that agree, low for things that oppose, has powered this whole AI revolution. But it also creates a massive blind spot, right? I mean, what if something pointing in the exact opposite direction is actually just as relevant, just for a different reason? And this is where the genius of this paper comes in. It introduces a totally new, more flexible geometry for how AI can focus. And the way they do it, it's just beautifully simple. And there it is. That's the one-line upgrade. Standard attention compares what it's looking for, the query, with a piece of info, the key, using a dot product to see how well they line up. This new idea, called expressive attention, does the exact same thing, but then it just squares the result. That's it. You just add a little power of 2. A tiny change with absolutely massive implications. So what does squaring it actually do? Well, it completely changes the game. Suddenly, the AI gives high attention to signals that are pointing in the same direction and to signals that are pointing in the opposite direction. In other words, strong agreement and strong disagreement are both seen as important signals. The only time attention is low now is when the signals are totally unrelated. The AI can finally see nuance in both harmony and opposition. And here is the absolute best part. This is the kind of thing you almost never see in AI development. This huge upgrade in how the model understands information, it costs nothing. 0 extra compute, 0 extra memory. It is, for all intents and purposes, a completely free performance boost. Okay, so it sounds amazing in theory, right? But does it actually work in practice? Well, the researchers set up a head-to-head showdown, expressive attention versus the old-school dot product attention, on a bunch of really tough tasks. And the results were, well, they speak for themselves. On a pretty simple task, you can see the standard DPA model, that's the maroon line, it just struggles. It gets confused, it can't figure it out. But the blue line, our new expressive attention model, it's a clean, steady shot straight up to 100% accuracy. No contest. Then they really cranked up the difficulty. And look what happened. The standard DPA model hits a hard wall. The paper calls it a local trap. That's when a model finds a decent but wrong strategy and just gets stuck there. It can't improve. But the EA model, it just blows right past that trap, keeps on learning, and pushes all the way to 100% on a problem the other model found impossible. This is so cool. Here we get to look under the hood. On the left, that's expressive attention. You can just see the difference, right? It's got this huge dynamic range, these intense bright reds and deep purples. It's being really decisive. Now look at the right, the standard DPA. It's all kind of washed out, a lot more muted. You can visually tell that one model is processing information with a lot more confidence and expression than the other. So, okay, a simple squaring trick makes AI better at tough problems. But why is this such a big deal? What does this actually mean in the real world? So let's just pull this all together. Expressive attention just flat out beats the standard method on complex stuff. It helps models get out of those learning traps we saw, which lets them solve problems and hit 100% accuracy where the old models just get stuck. And the best part, it does all of this for free. No extra compute, no extra memory. This means it's way better at handling tricky real-world situations, like spotting rare events, which gives it a huge practical edge. This quote from the paper really says it all. For the exact same size model, expressive attention unlocks a whole new tier of problem solving. It's not just a little bit better. It's the difference between a model that can solve a problem and one that literally cannot. And that just leaves us with this one fascinating thought to chew on. We're always on the hunt for the next big, complicated architecture in AI. But maybe, just maybe, one of the keys to unlocking more advanced reasoning has been hiding in plain sight this whole time, disguised as one of the simplest things you learn in math class, just squaring a number. Makes you wonder what other simple tricks are out there, right?